Yeah, so I plan to split it in two parts. So the first part is about ordinary differential equations. So just a quick recap what an ordinary differential equation actually is. And then we go into this kind of sensitivity analysis, so how to compute derivatives of solutions of ordinary differential equations. And specifically, we'll pick out one very important of these methods. So yeah, an ordinary differential equation is basically described by this kind of initial value problem where we have the state at a given initial time, t0, is equal to u0. And then the dynamics of this state is described by this kind of time evolution. So we have that the derivative of u is, the time derivative of u is equal to this function f that can depend on time, on the state itself, and on some parameters p. And the first natural question to ask is basically, how do we solve such an ODE? And let's say the probably simplest ODE I could imagine basically is one of a free-falling particle or ball, which is described by, well, probably I've all seen this, by Newton's law, is something like the acceleration is equal to minus the gravitational constant. And for these kind of easy ordinary differential equations, right, we can solve that analytically. So we simply integrate that equation twice, right? So we have that z prime is equal to some offset minus g t minus t0. And then we could integrate it a second time and we get like the full analytical solution of the height in that case with respect to time. Here on the slide, I did already something that's very meaningful, like to solve ODEs numerically. And that's like we want to bring down this kind of ODEs, which are sometimes described like with second order derivatives, to like just first order derivatives. And the basic trick is to introduce this additional variable v, right? So the velocity in that case, which can be written as, right? So v of t is equal to dz of t dt. Okay, so for that kind of ODE, we know the analytical solution, and it's basically easy to solve. Now coming back to the more general case, where we have some nice function f, but like solving for the analytical solution is tough, right? Because integrating is already tough, and solving these kind of initial value problems is even tougher. We can fall back to some numerical routines basically to solve it. And the easiest numerical routine is called Euler's solver, where we, and probably all of us could have come up with that like by ourselves. So we simply discretize time. So we introduce this Tn discrete time steps of our solution. And then if we plug that into the definition of the derivative, we get something like this finite difference equations. So right, if we see here the du dt would be un plus 1 at the, so that's basically the state at the time tn plus 1 minus the state at the time tn divided by delta t. And if we bring the delta t and the state to the other side, we get this explicit Euler method.
And last week we talked about finite difference approximation. So this is exactly taking that derivative and making a forward difference approximation.
Yeah, exactly. And you can have more sophisticated methods, of course, like to solve your ODEs. But for the rest of today, it's basically enough to just think of, if we don't know the analytical solution, we can use some numerical routine to solve for the state as a function of time. And yeah, actually, I wanted to implement that very quickly with you, like for the case of the free-falling ball, so like for that kind of ODE. So let's define some initial height, some kind of initial velocity, the gravitational constant, and well, maybe let's say that's basically our parameter g. We can say our initial state, right, is then this vector where we stack together initial height and initial velocity. And we say maybe in our task, we want to integrate that equation from some initial time to some final time. And we have to provide this kind of time discretization. Let's choose some small time discretization. Everybody's happy with that so far? So then we want to define our ODE function, so which is also called the vector field, where we just insert the definitions I had on the slide, basically. So we have that the derivative of the height with respect to time is the velocity, right? Which is here in our case now the second component. And we have that the derivative of the time is equal to, the derivative of the velocity with respect to time is equal to minus g, which is on the right-hand side of the board. And then we return basically, again, the vector of these two.
We're going to get g from the parameters, p1.
Oh, yeah. Let's say it like that. Thanks. And so now we want to implement our Euler solver, which should take, the kind of function that we want to solve. We want it to take the initial condition. Let's write a bit more down. The time span of the simulation. T-span. Yeah. And the parameters. And maybe even dt. And let's say our time at some point will be, so we make a copy so we don't overwrite into the array, so that this is preserved. We make a time grid. Is it actually big enough on the screen for everyone? Oh, cool. Right, we have to be a bit careful with the endpoint because we don't want to step one too far. And then the update rule is basically we take u at a given time, and that's, whoops.
And you don't need the deep copy since you're not overwriting u in place anyway.
That's true. I think I will need it later for one modification.
But you don't need any copy.
That's also true. Okay. And let's say I'm not interested in the full solution as a function of time, but just in the endpoint. Okay, let's see if that works already. Right, is that? Here should be a TI for sure. Yeah, we can check if that's the correct solution by plugging it into our analytical equation. Let me just pull the file. Right, so we have now written a numerical routine that spits out the state at a given time t, and I think that looks actually good. So we have t equal to 0, so our z should be z0 minus g minus v0 times 1 plus v0 times 1 minus 1/2 times g. And yeah, that looks basically good. That's a discretization error of the Euler method. And we could check the same for the second component.
Yeah, so the correct answer is 0.1, and then it's 0.105.
Yeah, exactly. It's slightly off because we have not the most sophisticated numerical solver. Okay, cool. So that's how we solve ODEs numerically if we don't have an analytical solution. And yeah, now we get into the kind of sensitivity analysis if we have numerical routine available. So there are two different ways, or fundamentally different ways to do sensitivity analysis. One is called discrete sensitivity analysis, and one is called continuous sensitivity analysis. And the first one is basically you imagine that you wrote that solver that we just wrote in some language that's compatible with automatic differentiation. And so we first discretize basically the task, and then we differentiate it. And the second one is basically we write a custom rule for the sensitivity analysis. And so we first approximate basically the gradient that we want to compute, and then differentiate it, and then discretize it. And for each of these methods, like these different paradigms basically, of in either first discretizing and then differentiating, or first differentiating and then discretizing, there are two different modes that you also probably have covered in the lecture already. You can either derive a forward, or also called tangent mode, or reverse adjoint modes. And depending on if you have many input parameters and a small number of outputs, one of these modes is basically preferred to each other. So in the setting where you have many parameters with respect to which you want to compute a gradient or derivative, you usually want to have some adjoint mode. And if you have high memory demands, you typically want to have like these continuous sensitivity methods. So it's a very relevant case to consider these continuous adjoints basically. And that's what we'll do today. So what are sensitivities good for? Just as a recap. So sensitivity analysis basically just describes what it says. So we might be interested in just describing how maybe the height of our ball would change if we slightly perturb the parameter of the differential equation. But we can also use the gradient of these ODEs to do more fancy stuff, as Stephen mentioned, like parameter estimation in chemical reaction networks or so, or like control for whatever physical system or chemical system you have at hand. So once again, so for the free-falling particle, it might be the task that we have some terminal cost or so. That could be this g of u at the final time. And we're interested in maybe saying how the height changes with respect to the gravitational constant. And so the claim is that this is always easy if we can solve the ODE analytically, right? So if we look at the solution there of the ODE, can someone say what's the sensitivity that I wrote down? Like the sensitivity of the final height with respect to g? Yeah. Yeah, exactly. So and now we will basically cover how we do that if we don't have the analytical solution available. For this, we will have to do some derivation. Yep. Let me move that. So we do continuous adjoints today. So let's first write down one of these cost functions, which I just had, in a bit more general way. So we have some cost that depends on the state as a function of time and p, where the state itself, of course, also depends on the parameters. And we say that this function can be written as the right, so we say we can, we don't have maybe just the final value, but we are interested in general as some functional of on the solution of the differential equation.
Are you going to think of capital G and little g as just being scalar functions?
Yes, yeah. And now comes basically the first nice trick in this kind of derivation, and that's related to Lagrange multipliers. Yeah, probably a good idea. Right, such that I see. Okay, so the first trick that we want to do is basically to add a 0 to this kind of function. So
if you pause here, make sure everyone understands what you're doing. So you have some ODE, you solve for u of t, okay, and then you're going to compute a number at the end, capital G, by taking the ODE solution and integrating some function little g to that solution. Right? And the ODE depends on some parameters, and you want to find the derivative of this final output, capital G, with respect to all those parameters of p. So little p might be a vector of parameters. It might be 10,000 reaction rates. Capital G might be the integral of the square difference between the ODE solution and like some experimental data on the chemical reaction concentrations.
yeah, exactly. Does everybody see why that's a 0? No? Right, so why...
Yeah, sorry, I was talking about that and maybe you already need to say what the 0 is.
Right, so because by definition, basically, our state fulfills this ordinary differential equation, we can introduce this kind of Lagrange multiplier, and that term is 0. So if we add that term to this kind of cost function, we basically do nothing. But we have this free Lagrange multiplier that we can choose later on. So that will be kind of the trick that we will play. And now, as Stephen already said, so we're interested in computing dg over dp, right? So that's a kind of sensitivity gradient information that we want to have. There will be a long line. So what we basically do is just doing now the chain rule on that term and these terms.
For now, think of p as a scalar, but in general, it could be a vector or something, and it's a gradient instead of dg. Probably this is a gradient transpose.
Yeah, it's a gradient transpose. Yeah.
It's what we were calling G prime.
Yeah, let me quickly write it down because it's easy to do mistakes on that part. Oh, -9 from a minus above. Okay, I leave out the UTPs to save some space, but every U here depends on T and P. I guess that's maybe hard to read at the end. So there's a DT only missing here. Is that still readable for you on that side? I don't know. I will repeat that term in a second, so you will see again what's that term. Right. So let's call that basically like the sensitivity. Call that, and yet let's simplify a bit the notation. So that's my small g. I'm sorry, my small g's and small f's look fairly similar. That's small g u. So I always denote by subscript the, well, with respect to what we differentiate.
This is like in the homework. We also ask you a problem. Partial derivatives are subscripts.
Small gp. And in this term, what we can do here is basically swap the derivative with respect to p and with respect to time. So we get here s prime, right? So because when we swap it, we have the udp, which is s, and then we have the time derivative. And we have here some fu times s, and the last term is that last term is fp. Okay, let me go to the center because I think it's probably better readable from there.
Can you scroll the board down so you can see the whole?
Oh, yeah. Oh, okay. Oh, yeah, okay. So, yeah, I write the second term, which was probably hard to read, a bit bigger. So that's the second term on the right-hand side. And
can I maybe say something to try and clarify?
Yep.
So you have this function that you're trying to differentiate. And if you just differentiate with respect to p directly, you get this term, which is easy. Right? If the function depends directly on the parameters, you can take that derivative. Often that derivative is 0. This term, which is easy, this is your cost function, how it's dependent on the solution. This term is hard. Like, how do you get the derivative of the solution with respect to the parameters? So the goal in adding 0 here is going to give us this extra degree of freedom lambda that, if he's clever in how he chooses this, there'll be a trick that allows him to cancel this term and get this term that's hard and get a differential equation for lambda. So that's, it's often good to sort of show, there's kind of a magic step here where you add this lambda term. And,
yeah.
It's sometimes good to not keep people in suspense about why the hell did you add this term.
That's true. Yeah, exactly. There's one step before we can actually do that trick to eliminate the s, and that's basically this s prime that we got, which we first have to get rid of. Anybody has an idea, maybe how to do that? Like turning our plan is to turn s prime into an s.
This is 1801 question. If you have a derivative in an integral you don't like, how can you get rid of it?
Integrate by parts.
That's, yeah. So we integrate that term by parts, and that gives us right, so that's from the integration by parts. Now the prime on the lambda, which will be exactly going towards the ODE that Stephen mentioned.
So prime is always time derivative.
Yes, yes, should have said that.
Shape of lambda, like why is lambda a matrix, a vector, a scalar? Why is it transpose? Like what's the size of this lambda?
Oh, the size of this lambda. So it's such that, right, this output should be a scalar, right? Because we optimize a scalar cost function. So the size of lambda is basically in the adjoint space of f, right? Or of u prime.
Yeah, so the solution here is not a scalar. U is not a scalar, it's a column vector. Right? You have n equations and n variables. Lambda is a column vector with the same number of components. It has the same shape as U.
Yeah, so what we want to do next is basically insert back this term into that equation. So that was our term here, and so we take now this part, insert it back, and we're already going towards our goal and reorder all terms such that we have this S separated, basically. So what we end up is basically this dg dp using a prime here. Okay, let's write that directly into 1. Okay, so not much happened here, basically. It's just looking at all the terms. So we leave that term here. This is that term. That is that term. We moved this term, which doesn't depend on f, to the front. And we had another term that was depending on s here, which we moved to the back, basically. So these two terms were like, swapped.
The goal here is the s, which is du, the derivative of the solution expected parameters. That's the annoying term you don't know how to deal with. So you're going to try and group it all together and then make that term 0 so you don't have to deal with it.
Yeah. So we're free to choose lambda. So we can choose lambda to be whatever we want. So why don't we take basically the choice lambda prime of t is equal to a minus lambda t fu minus gu, right? If we take that choice, we will have that this term vanishes. And we can also, since this is an ODE, specify, well, basically the initial condition. So we can specify that lambda of t should be equal to 0. If we do that, we have that this term cancels, and one of the terms from this integration by parts also cancels. Then it's the question of what?
Why did you choose capital T to be lambda capital T be 0?
Yeah, that's the next question, and that's because basically what is S of T0, which comes into that term. So we know that S of T0, right, by definition of S, it's the sensitivity of the initial state with respect to the parameter. And we know that the initial state doesn't depend on the parameter. So that term
could, right? You could, but whatever it is, you know what it is. Like you have the initial condition in closed form, right? So even if it depends on some parameters,
Yeah.
You know what it is. But here only you're simplifying it to only the system of equations depends on the parameters.
Yes. Yeah. Exactly. So either it's easy or it's 0, basically. Yes, nice. So we have, in the end, that just this term basically survives. So we have that dg, the derivative of g with respect to the parameters, or the gradient in this case, is equal to that derivative, which is easy compute. It depends on this lambda, and it depends on the derivative of f with respect to p. Oh, that's a Jacobian, basically. So let me let this here, right here. So what's kind of the procedure that we need to do to solve it, right? So when we solve that integral, we realize that we first have to solve this ordinary differential equation, which gets a special name, actually. So this is the adjoint ODE. But we also see that the forward solution is embedded in that ODE, right? So to solve for the quantity which we're interested in, we basically have a 3-step procedure. So we first solve for u of t. Oh, that's at least the easiest way to think about it. We first would solve for the ODE for u of t, then we have that information. In the next step, we solve for lambda of t. I could also
Can you write down the ODEs again and just these steps, just to summarize? You're solving an ODE for u of t. And write down the ODE for lambda, maybe. Maybe transpose it back, so just lambda prime. Usually you would transpose it, right?
Okay. Then it's
just transposing both sides of that equation for lambda. GU transpose. And there's an initial condition, right? So
yeah, so that has an initial condition. Right, the initial condition is kind of important because we see the first ODE we solve forwards in time, and then the adjoint ODE, as you are now used to probably from reverse mode AD, we have to solve backwards in time. So we have also this forward-backwards workflow. And then once we know u and lambda, we can actually solve the integration for dg dp.
Can you write that out? Just because it simplifies now, so
yeah.
Several of the terms have dropped out.
Which is G.
And write big.
Okay, that's a.
No, wait. There's no. I thought you want to write it in terms of lambda.
Oh,
right?
yeah. Oh,
yeah. There's no s anymore.
Wait, yeah, exactly. G. Yeah, that should be right.
And then plus a boundary. Oh, no, the boundary term is 0 in their case.
Yeah, I said it was 0.
So before you continue, let me just compare this. We talked about adjoint methods in class before, but for solving linear systems or nonlinear equations where where they depend on some parameter, and it was of the same flavor. So first you solve the forward equations. You solve ax equals b for x, right? And then we solved an adjoint equation that involved a transpose or a transpose of a Jacobian, right? But whatever the adjoint equation was of the same kind of same flavor and same size as the original problem, but it was linear, right? And then once you have the forward solution, the adjoint solution, you just take some dot products. So here you solve an ODE, right? You're using whatever your favorite ODE solver is. Then you solve an adjoint ODE, which is sort of transposed, and it's linear now, even if the original one was nonlinear, and it's backwards in time if the original one was forwards in time. And then once you have the forward solution u of t and the adjoint solution lambda of t, you take some dot products, which for functions, the analog of that is integrals, right? And so everything in that sense becomes easy now. Independent, even if you have 10,000 parameters, you solve one forward ODE, one adjoint ODE of the same size, and then some dot products. So this is why you can compute derivatives with respect to a huge number of parameters efficiently. And they're kind of always of the same flavor, these adjoint reverse mode things.
Yes. And now there are a few tricks basically to evaluate that efficiently, or like different styles to evaluate that equation. The first thing to notice is that basically that we don't necessarily, for this continuous adjoint method, have to store and compute the full continuous solution of u of t, because an ODE is basically reversible. And so we can solve the ODE forwards, just save the final value of that ODE, and then solve it basically in lockstep backwards together with lambda to have, well, to avoid this kind of storing the continuous solution of u of t at all times. And everybody happy with that kind of trick? Right, so
I'm not happy with that kind of trick.
Not
Like
happy?
if it's chaotic or something like that.
True, so
Solving
while
it forwards
ODEs are
might be
reversible.
exponentially decaying, and solving it backwards might be exponentially growing. So that trick doesn't always work. Right.
Yes, exactly. That trick has to be done with care. And there are some, right, so that trick, just to visualize it again, it basically says if we have some ODE at u to 0 and we solve it to some final time, u of capital T, I was saying you can just store this value and start solving it backwards. But yeah, depending on your physical system, well, your trajectory might not, because your numerical solver might not be reversible, you might deviate from your true solution. And then if you solve it for long times again backwards, that might be numerically very bad. And so the first thing people are usually doing is introducing so-called checkpoints, which only means once you solve it back and you reach your checkpoint, you basically reset your solution to the state which you had forwards. So that reduces a bit the memory consumption. And the second trick people are doing, if it's really unstable and your ODE solver is not working, then what you would do is maybe also have these checkpoints, but always just store a continuous solution within the checkpoints that you solved forwards again in time.
So just another comment on that. So one thing we have to be always careful about in presenting things is explaining the solution before you explain the problem, right? So the issue here that you're trying to solve with going backwards and reversing and so forth is, so in principle, you solve it forward, right, to find u of t, and then you solve it backwards to find lambda t, and then you take some dot products, right? The problem you can run into is that then you need to store u of t not just at the endpoint, but at all the intermediate times, which is fine if u of t is just a small number of parameters, and you just store it at a bunch of points, and then you you basically can interpolate with polynomials in between. Right? This is how ODE solvers work, right? But this is a problem if you're solving a huge system of ODEs, where say it's really a discretized PDE, for example. So you have U is, say, the electric field at every point in space as a function of time in some big computational cell. Then then usually when you solve it, you march it forward in time, and you kind of just only store the solution at the current time. But here, you need to store all the solutions at all the intermediate times, all the way until the end, and then go backwards. And you can run out of memory. And so this is the basic problem with adjoint methods, and when you have like evolving in time or going through big recurrences, is you need to store all the intermediate ones. And so there's all these tricks to try and only store some of the intermediate values at some checkpoints and kind of reconstruct things on the fly as you integrate ODE back, integrate lambda t backwards, so that you don't need to store everything. But that's sort of the issue that you're struggling with here. But for small ODEs to only have a few things you're going to need time, you just store the whole solution. It's not that hard.
Right, true. Yeah, or for small ODEs that contain some parametric function that's very expensive to evaluate, right? Like what Chris is basically doing is putting a neural network inside the drift function. So even if the ODE itself looks very simple, if you have a neural network in each time step, you will have to store all intermediate computations also and outputs of that. So yeah, that makes the discontinuous adjoint very meaningful. Yeah, right. So there's a third kind of trick which can be used to simplify that workflow even a bit more. Basically, that's the first trick, and as we now discussed, it's not always applicable, but if it's applicable, it can be nice and very efficient. The third trick is basically to look at this integration term and basically realize that an integration can also be phrased as a solution to an ordinary differential equation. So, not sure if that was covered already. But yeah, let's say I have a function f, want to integrate it as a couple of times, t0 to t. Right, everybody agrees that's kind of the same form. So we have some integration. And now the claim is that we can write that as an ordinary differential equation, small f of t. And yeah, now we want to basically apply Euler's method to that. And so if we apply Euler's method.
So wait, stop here for a second. So before you again give the solution, so you're going to write a differential equation w prime equals f of t, right? So wt is going to be a new variable. What's the initial condition of that you're going to want to use? Again, at the end, you're going to want to write down a differential equation whose solution gives that integral. So so you're going to write a differential equation dwt dt equals little f of t. What initial condition should you use? Any guesses? To turn it back, so its solution will give you the same thing as that definite integral from t0 to t. Zero. Okay, so put at what time? At t naught. So w t naught equals 0. And then what's capital F of t equals what then? So now the integral you want, the first line, capital, is that an I or an F? I can't.
That's an F.
That's a capital F. Okay.
Sorry.
It has the second line going. Okay. So anyway, so your capital F of t, your integral that you want, is what in terms of w? So if you have a differential equation, its initial condition t equals 0 is 0. T0 is 0. Its derivative is the f of t. So then the integral is what now?
Yeah, right. So I can write that integral. Let me write one step in between, basically in kind of slightly.
You're kind of discretizing it first. So before you discretize that, I want to make sure they understand the connection between the ODE and the integral. So don't discretize it yet, right? This is an exact relationship, right?
Oh, so just want to have plugged in the w.
Yeah. It's w of what? No, there's no integral. It's equal to w of. It's w of capital T, right? That's.
Oh, okay.
Right.
Now I see what you want to do.
Right. So the point is, if you have a differential equation w prime equals ft, the solution is just the integral. W is just the integral of f, which is what you want, and then you put the initial condition t0 equals 0. That's your left edge of the integral, and then the final integral you want is just w of t. So that's he's turning the integral you want is just a differential equation. Is this differential equation? Now you're going to discretize it, right?
Right. Now, if I'm discretizing it, I would see the same basically as for an Euler step. Should I write it down?
Sure, if you want to discretize it. Yeah, but I just wanted to, because not everyone here has done a lot of differential equations, right? Or maybe hasn't done them recently, so I want to make sure they understand.
Okay.
Understood that trick. Just go, take it all the way up.
Okay. Right, so I'm basically writing down what the Euler steps would be in the discretization for that integral. That's the first, and then I could just keep iterating. Let's think a moment forward. So these are n Euler steps iterated on the function. There's an I missing probably somewhere. Right, because once I have my first step, the time changes, and then that's plugged back also into the function.
So this is really an approximation for the original thing, right? So you're writing equals here, but just to be clear, right? The original equation is you have an integral and the differential equation. That's an exact relationship, and now you're going to write the discrete analog of that, or the discrete approximation. So w of t plus delta t is really approximately equal to w of t plus t delta t, and this is approximately.
Basically, if I do again something like an Euler step.
So you can approximate the derivative by a difference, and then the integral is essentially approximated by a sum.
Right, and so this now has then also the typical form of what you would do numerically to solve an integral, right? So it's you have the function value at different points, and then with the discretization that you use, and sum that all up.
This is a very simple way to do an approximate integral numerically. Just like Euler integration for ODEs, and this approximate sum for an integral, you should never ever do this in reality almost, because there's exponentially more accurate ways to integrate approximate integrals. But it's a nice way to really simply think of if you're confused by integrals and derivatives, that you can think of them as differences and sums, or sums and differences.
Right. Yeah, right. That statement is true for both, right? The Euler solver for ODEs and the kind of derivation for the integral. Oh. Yeah, that's actually the full derivation.
Yeah, so does everyone see that basically then if you plug in the initial t is 0, wt0 is 0, right? So, why don't you take it one step further? So then wt0, if wt0 is 0, the first term is 0, the second term is approximately the integral, right? So it's just restating the same thing, just with sums and differences. So this is so the solution of the ODE is really the integral.
Yes. To summarize that, so we can have then basically all the three methods above.
Wait, can you finish and write? So the point is, what you're going to do then is just merge the solution of the adjoint ODE with that integral in the third step. So instead of doing them in separate steps, so you can maybe just write down the derivative. It has a.
Right?
Yeah. So what's w? So w is now going to be. W is going to be lambda and. Okay, but it doesn't matter.
Depending on.
You want to go in the other direction, right?
Probably want to solve it like that.
But the point is, you think of this as a coupled ODE. For w, along with the adjoint ODE for lambda prime. So if you write down the lambda prime underneath, right?
GU.
So you can think of this as one system of ODEs for a vector that contains W and lambda, right? So you just do the two things together instead of as separate steps. Oh, and then I guess you could also you could also integrate the original equation backwards as well. Right. So now your unknowns are W, lambda, and U. It's like one big vector of those three things stacked together. And the advantage of this is that you don't need to store the lambdas, I guess, and maybe the u's if you were able to integrate the whole thing backwards.
Yes.
So you don't need to store anything. You just pass this to your ODE integrator, and it only keeps track of your current step, and it just walks from beginning to end. And at the end of the day, your W is the integral that you want. Is the derivative.
Exactly. So that's the most memory efficient one to basically solve for the sensitivity dg dp in the end. Right.
So I think we should maybe take a break in a minute. But are you basically, is this basically it, or are you going to show some examples?
I would have the integration of that numerically, but it takes another 10-15 minutes at least.
Yeah, I see. You want to show an example of. Yeah, I mean we can do that after the break, but maybe we can just take a break for a couple minutes now. But do people have questions about this step? You have forward ODE, adjoint ODE, and then a dot product, which is basically an integral. And then there's these tricks to try and basically combine them into one ODE that you solve instead of having to store U of t, store lambda of t, and then do the integral.
So say you have like a set data point that you're comparing solution to some ODE for. Would you, so if the system's like not chaotic, you probably want to start at like the final data point and integrate backward with the lambda equation. But if it is, then would you just want to integrate forward to get the full solution and then just solve the adjoint equation afterwards?
Yeah, so suppose capital G, maybe we rephrase it. Suppose capital G is a sum and not an integral, right? So you have a bunch of delta functions, another way of thinking about it, right? So basically, you're comparing the solution U of t to, say, some known solution, some measured data, at only a discrete set of times. So now G is a sum, right? So one way to do it would be to compute U of t, lambda of t, and then just do the sum. But is there a way to combine that into a single ODE if now capital G is not an integral, it's a discrete summation over a set of times?
Yeah, basically you can write it, go to this kind of discrete formulation. The probably easiest way, I think, to think about it is that these describe the kind of continuous changes that you want to have in the cost function. And so what you will have if you just have your cost function compared at discrete time points. You basically have your solution, and then at some points you compare your cost. And so what will happen is that you will have a backward solution starting from here for the adjoint and for you, and then at these time points where you have your comparison, you basically you can update your state by the change that comes in just from those nodes, basically. So you will just have like a partial derivatives added at those time points to your adjoint state.
Yeah, so I mean, ODE solvers, you can tell them to stop at certain times. So as you go backwards in time, you could just have it stop at that time and then update something, and then stop at that time and add something, at the next time and add something to you accumulate your sum as you go along. But like mathematically, you could basically think of it as jump conditions that occur at those times. And so there's also ways to include those in in differential equation solvers, where every once in a while, these times something jumps. There's a discontinuity in the solution, and then in between, it's not changing at all in this case.
Yeah.
Probably it's easier just to say, let me integrate it and up to this time, get that solution up to the next time, and just have a callback at those discrete times and just accumulate the sum.
So maybe cycling back to the idea of matrix calculus. So here everything is still basically, if you want to generalize it, say you have a matrix valued ODE, then your lambdas become like some matrix valued thing. So they just like basically live in the dual space to whatever you want to take the derivative of. And as long as it sort of makes sense, the ODEs that come out at the other end, that will give you like the right sensitivity. Is that?
Yeah. So if you have a more general space, so U lives in some arbitrary vector space, right? Then you have to replace the lambda transpose there with an inner product, right? And then this FU transpose is some more general adjoint operator in that Hilbert space. Right, so all of this still works. So you can think of this as just, it's literally the same derivation. You can think of it as just a change. It's just lambda transpose is now notation for that inner product. I mean, you understand what the notation means in a more general sense, but it's literally the same thing. I don't know. Have you done anything where, I guess you're doing quantum systems, so probably your states live in some more
density matrices. Yeah, sure.
Live in more general Hilbert spaces all the time.
Yeah. Yeah, numerically you can also then vectorize the density matrix, right? And they have like, rewrite basically also the definitions of F to deal with vectors depending on like your implementation. But yeah, right.
So we talked about that as well. So one way of dealing with matrices and other things is just turn them into column vectors, right? But if it's more natural to in your Suslin space to talk about matrices, then you'd really rather deal with that Hilbert space directly.
Right.
And if these are PDEs, so U is now not is like a function of space, right? Of course, on a computer you probably discretized it, but it's nice conceptually to think about this as a function of space, and this inner lambda is also a function of space, for example, and then this inner product is some kind of integral over space. So it is really powerful to be able to not have to turn everything into a column vector when you want to do linear algebra. A 5-minute break, so we'll come back at 12:10, and I could go then, or if you want to show some more examples, you can do that. But.